Hello students, welcome to the calculus course. In this lecture we will talk about formal definition of a limit. So this definition is very important. Unfortunately it's very hard, it's hard to use, but we still need to go through to understand the formal mathematical definition of a limit. Alright, so again, the limit the limit of the function f when x approaches a is equal to L. And we read it as the limit of f of x as x approaches a is equal to L. That's how you read it, is equal to L. All right, so basically what does it do? It describes the behavior of a function of f of x for x close to a. For x close to a. Okay, and close to a, but I forgot to add, but not equal to it. That's really important. We discussed it a little bit, but still I'm going to add it up. All right, so time to formally define it will be really strange at first, but let's try to deal with it. So we say that limit of f of x when x approaches a is equal to L if and only if, but for this if and only if, in the future we'll use a special symbol that's this double arrow. So if and only if, now the strange part. And I will explain all of the symbols in a second. So this is a Greek letter epsilon. Maybe I'll start explaining it on the left. So this symbol, it says for all values, or some people think for any, right? Either this or this, or for any, right? But it's pretty much the same thing. And this letter is Greek letter epsilon. So it says that for all values epsilon greater than 0, then again, strange symbol. This symbol means there exists. All right, there exists delta greater than 0 such that 0 less than an absolute value x minus a less than delta. Oh, I didn't really say this is Greek lowercase delta. So there such that as soon as 0 is less than x minus a in absolute value less than delta, would imply that f of x minus L is less than epsilon. Okay, so let's talk about the meaning of all of this, which doesn't make sense. But before we talk about meaning, let me read it from start to finish, because I was moving back and forth trying to explain the letters, but let's read it from start to finish. So we say that the limit of f of x when x approaches a is equal to f to L if and only if for any epsilon greater than 0, there exists a delta greater than 0 such that when 0 less than x minus a in absolute value less than delta would imply that f of x minus L is less than epsilon. So these are like very, very fancy way to write a very simple idea. Simple idea tells you the following. If you have some kind of a curve, and you have the value a on the x-axis, we say that the limit will be L. When we're pretty close to a. But what all of this meaning over here is really straightforward. Basically, it tells you, I tell you, you give me any epsilon distance that you want to be close to L. So it means how close you want to be to L. That's the epsilon. All right, so you tell me, I want to be this epsilon close to L. So basically, if this is your L over here, then this distance over here, this distance over here is epsilon. So basically, you are within epsilon distance of L. And over here, you also have an epsilon. So what would be this point over here then? This point over here will be L plus epsilon. So this point is L plus epsilon. And this point on the bottom is exactly L minus epsilon. So you created a little interval around L that you want to be inside of. So you created this epsilon and you created this interval within L. So you created this interval within L. So you want to be that close to L. And my task is to provide you the interval around A. So my goal is to provide you the interval around A such that when you pick any point over here and you come down over here by using your function, this point will be close to A. So now I have to select this interval on the x-axis. And I will call this distance on the right to be delta distance. I will close this distance on the left to be delta. Then this point over here will be A minus delta, and this point over here will be A plus delta. So you give me epsilon, I have to provide you delta such that no matter which point you choose within this interval over here near L, it would fall by using the function into this interval within A, this delta interval near A. All right, so let's try to put this all together. So if I choose x greater than A minus delta and less than A plus delta, you can clearly see over here that I can subtract A from all three parts. So here and here it goes away. So this implies that x is greater than negative delta and less, oh, forgot the A, and less than delta. All right. But basically this means negative delta is less than x minus A and x minus A is less than delta. And here, if you multiply by -1, we're going to get delta is greater than negative x minus A. All right, but if we rewrite this, and maybe this one first, I will reverse and write it negative x minus A is less than delta. So this was the first part, and the second part says x minus a is less than delta. All right. Okay, but this is exactly this expression, x minus a is less than delta, and obviously this quantity is always greater than 0 because x cannot be equal to a. All right, so this would be this part. And this part follows very similarly. So basically a fancy way to write the following idea. You give me an epsilon distance that you want to stay within L. I give you delta such that you would stay within A, and if you pick any point in this interval, you will move up, and you will arrive over here within the epsilon interval near L. But again, if you oversimplify it, that means when we're close to A, we're close to L. All right, but this is a formal definition of the limit. Okay, so let's try to use it to solve some problems. Let's try to use it to solve a problem. So use the definition of the limit to find limit of 2x plus 1 when x approaches 3. Okay, so let's try to solve this problem. The first step you have to guess your answer. Guess the answer. So how do you guess the answer? You take x equals 3 and you plug it into the function and see if it's going to work. And if it's going to work, then it will be fine for us. And this idea will be very crucial to us in the future. So we're going to take x equals 3 and we're going to x equals 3 and we're going to plug it into 2x plus 1. So it's equal to 2 times 3 plus 1, and if we calculate it, we're going to get 7. So we guessed our answer, we know this will be 7. Then set up the definition. So what do we have to set up? We have to find the value of a, and in our case x goes to 3, so a is equal to 3. You have to write your f of x, which is 2x plus 1, and you have to write your L, which is equal to 7. So let me try to write the whole definition over here. We say that the limit of f of x when x approaches a is equal to L if and only if for any epsilon greater than 0 there exists a delta greater than 0 such that, that's a short way to write such that as soon as 0 is less than x minus a less than delta would imply that f of x is really close to L. All right, so let's plug everything in that we have. So we have a limit of f of x, so it's 2x plus 1 when x goes to 3 is equal to 7 if and only if for any epsilon, we cannot do much with epsilon, greater than 0, there exists a delta greater than 0, such that. Now we can do something here. So x is just a variable, so it stays. For a, we put 3. Then we put less than, and for delta, we put delta. Implies, then for f of x, we write what it is, so it's 2x plus 1. For L, we write what it is 7. And it's less than, oh, mistake here, less than epsilon here, definitely, less than epsilon. All right, so that was the setup. Now step number 3, start from the end. What do we mean start from the end? Take the last expression over here. So we take absolute value of 2x plus 1. Let me finish the phrase though. Start from the end and pick and set your delta. Set your delta. I'll explain in a second what it means. So we're starting from the end, so 2x plus 1 minus 7 less than epsilon. And we start writing it one under another. So let's try to see how it's going to work. So we simplify it first, so it's 2x minus 6 if you subtract 1 and 7 less than epsilon. Then you can clearly see this is 2, but 6 is 2 times 3. So we can take 2 and we can factor it out. So we'll be left with x minus 3 if we factor 2 correctly. Then we use the rule for the absolute values. For the absolute value, we have this rule that absolute value of a times b is equal to absolute value of a times the absolute value of b. So we have absolute value of 2 times the absolute value of x minus 3 less than epsilon. But we can clearly see that the absolute value of 2 is number 2, x minus 3 less than epsilon. Then we can divide both sides by 2, and we have absolute value of x minus 3 is less than epsilon over 2. But if I go back to what we want to show, this is exactly this part. Look. This is definitely greater than 0 since x cannot be equal to 3, right? X cannot be equal to 3. It cannot be a. So it's always going to be greater than 0 because if it's negative, the absolute value will make it positive. So it cannot be equal to 0. So it's always greater than 0. And on the right side, it's less than epsilon over 2. But let's go back to the definition. We want this absolute value of x minus 3 to be less than delta. So what should we choose our delta to be? If we choose delta to be this, everything will work. So we can say set delta equal to epsilon over 2. Then 0 is less than x minus 3 in absolute value, less than delta. Now, we will gonna reverse the steps. It would mean this, and this would mean this, and this would mean this. And this would mean this, and this would mean this, which would mean this, and then you will be all set because that's exactly what we wanted. This means this. So we proved it. Again, very complicated idea, but in real life, for the simple equations, for simple functions, it's really easy, but for complicated ones, you have to take a high-level class in mathematics in order to do those. So we're going to deal only with linear ones, so it's not going to be a big deal. All right, so you give me epsilon, I'll take epsilon, I will divide by 2, I will set my delta to this quantity, and then everything will work. As soon as you take x within the delta distance near 3, then your f function will be within 7 of epsilon distance. All right, so before we end this lecture, let's do one more example because, again, this is a complicated idea. So another example is this one. The assignment wants us to find the limit of 3x minus 1 when x approaches 2. So again, our first step is to guess the answer. So we're going to take x equals 2 and we're going to plug it into the 3x minus 1. So it's going to be 3 times 2 minus 1. So it's 6 minus 1, so it's 5. So we guess our answer. Second, we set up the limit. So to set up the limit, we have to provide a, and our a is 2. We have to provide f of x, which is 3x minus 1, and we have to provide L, which is 5. All right, so we're setting it up. So we say limit of 3x minus 1 when x approaches 2 is equal to 5 if and only if, again, strange symbols. For any epsilon greater than 0, there exists a delta greater than 0 such that as soon as 0 is less than x minus a, so minus 2 is less than delta would imply that f of x, which is 3x minus 1 minus 5, is less than epsilon. Again, we're going to start from the end. So we're going to take 3x minus 1 minus 5 less than epsilon. Minus 1 and minus 5 give us 6, so we have 3x minus 6 is less than epsilon. We're going to factor 3 out, so we factor 3 out, so we're going to get 3 times x minus 2 is less than epsilon. Then we use the rule for the product for absolute value, so it's absolute value of 3 times the absolute value of x minus 2 less than epsilon. Okay, so let's do this out. Absolute value of 3 is just 3. We have x minus 2 here, less than epsilon. We divide both sides by 3 to get that absolute value of x minus 2 is less than epsilon. And, epsilon over 3, obviously. So let's look. This is exactly what we wanted. This term is definitely greater than 0 because x cannot be equal to 2, right? This means goes to 2, but not to itself. And we need to choose a delta. Look, this would be a good choice for delta. So we'll say set delta to be epsilon over 3. And this would imply that 0 is less than x minus 2 in absolute value less than delta. And this would imply this, and this would imply this, would imply that, and would imply that, and it would imply this, which would imply that. So we proved it. This implies, look, this is exactly like, there's exactly the same, right? Like exactly the same. And this term implies this term. So, well said. And so this is a way to use a proper definition to figure out limits. So next time we're going to continue developing these ideas for limits, and I'll see you in the next lecture.